of subject engineering mathematics, chapter 2 differential equations. Now in this session we continue some basic formulae related to integration followed by concept. The concept is solving first order first degree differential equations. In the last session we have discussed 14 formulae of integration. Now let us discuss formula number 15 of integration. It is integral e power x into f of x plus f dash of x dx. Integral e power x into function plus f dash, where f dash represents the first order derivative of this function. Now this is nothing but e power x into f of x. Now this is my original function f of x. This is its first order derivative. So when you integrate this function e power x into function plus its derivative, then the result is e power x into f of x. It is very simple to verify. When you find the derivative of this function, by product rule, the answer becomes e power x into f dash of x plus f of x into e power x. Apply product rule to get the derivative of this. E power x into derivative of this plus this into derivative of e power x is e power x. This is nothing but e power x into function plus its derivative. So therefore, when you differentiate this, we are getting e power x into function plus its derivative. What does it mean? When you integrate this function with respect to variable x, the result is e power x into f of x. Now let us take few examples. Suppose I have integral e power x into sin x plus cos x dx. Integral e power x into sin x plus cos x dx. Now here I assume that f of x is sin x and f dash of x equal to cos x. So it is in the formula number 15. According to this becomes e power x into sin x. Another useful formula is if I have integral e power x into log x plus 1 by x. Integral e power x into log x plus 1 by x dx. Now this is f of x and this is the f dash of x. 1 by x is derivative of this. So according to rule number 15, the result is e power x into log x. E power x into log x. Note this. Now let us discuss formula number 16. In fact, this is last formula in integration. So this is integral f of x into g of x dx. Integral of product of two functions. In the last session we have seen integral k1 into f of x plus or minus k2 into g of x dx. So when you have plus or minus symbols between two functions, you can split the integration. See, suppose if I have integral x square plus cos x dx. So that is equivalent to integral x square dx plus integral cos x dx. When you have two functions, in between two functions, if I have either plus symbol or minus symbol, split the integral by inserting the same symbol. That flexibility is not there for multiplication. Now in this case, what we do is, we need to simplify this so that we need to calculate integral of a single function. It becomes, in order to get this formula, I can take this f of x outside integral or g of x. That depends on nature of these two functions. Suppose I am taking f of x outside. So f of x into integral g of x dx minus integral. Here f of x is taken outside integral, so find the derivative of this. This is integral f dash of x into, the same integral will repeat here also. So this is integral g of x dx whole dx. So what we have done is just one function is taken outside the integral. So by keeping second function inside the integral minus it is taken before integral, so find the derivative of this into again same integral g of x dx again dx, or this is equivalent to g of x into integral f of x dx minus g dash of x into integral g dash of x into integral f of x dx whole dx. So either in this case or in this case you get integral f of x into g of x dx, and this formula is called integration by parts. This is called integration by parts. Let us take a simple example. Suppose I want to calculate integral x into e power x dx. Now this is in the form integral f of x into g of x dx. Suppose I can apply either this or this, but let us see if I apply second formula, what is the difficulty in this case. If I assume that this as f of x and this as g of x, so take e power x outside, then integral x becomes x square by 2 dx. That means unnecessarily we are increasing the powers of x. Therefore take x outside integral, then when you differentiate this, the power will be reduced. So therefore when you are applying integration by parts, if either f of x or g of x is a positive integral powers of x, better to take that function outside the integral. Then the result will be so simple. That means when you differentiate x power k, the result is k into x power k minus 1. Power is reducing by 1. But whereas when you when you integrate x power k, the powers will be rising. So what is our task is, gradually we need to decrease the powers of x, so that my job will be very simple, right? So when you are applying integration by parts for two different functions f of x and g of x, if either f of x or g of x is a positive integral power of x, better to take that function outside integral. Then powers of x will be gradually reducing, finally it reaches to some constant value. Got it? Therefore in this case I will take x outside integral, so x into integral e power x dx minus integral, the derivative of x with respect to x is 1 into integral e power x dx whole dx. So this is x into integral e power x is e power x minus integral e power x dx is e power x. Now this is x into e power x minus e power x. So the result is e power x into x minus 1. Here the power of x is 1. That's why we have applied integration by parts a single time. Suppose if I have this integral x square into e power x dx. So in this case the power of x is 2. So we need to apply integration by parts 2 times. In simple words, the result will be like this: e power x into x square. The derivative of x square is 2x. The derivative of 2x is 2. The derivative of 2 becomes 0, so you need not write. So first you can have plus symbol minus plus symbol. So therefore indirectly we have applied integration by parts twice. Note these points. Now with this we have finished basic formulae of differentiation and integration. Now let us actually enter into the subject. In this session, we discuss the basic concepts of first order and first degree differential equations. Now let us briefly discuss what we are going to see in case of differential equations. As we have seen in the last sessions, generally differential equations are of two categories. One is ordinary differential equation, another one is a partial differential equation. If it is ordinary differential equation or a partial differential equation, we have a single task, that is solving the value of dependent variable in terms of independent variables. So finding the value of dependent variable in terms of independent variables is nothing but solving a differential equation, right? So we have different techniques to solve first order, first degree differential equations. First of all, let us look at the general form of first order and first degree differential equations. So the concept we discuss in this session is first order and first degree differential equations. The general form of first order and first degree differential equation is dy by dx equal to f of x comma y, or equivalently we can write mdx plus ndy equal to 0. So either this or this is called a general form of first order and first degree differential equation. Dy by dx equal to f of x comma y. Here we have only one derivative, its order is 1. So it's a first order first degree differential equation. Even that is the same equation is equivalent to mdx plus ndy equal to 0. Very simple, you cross multiply this equation, rearrange all terms, that equation will be reduced to this mdx plus ndy equal to 0. Now what is this f, what is this m, and what is this n? All these are functions of two variables x comma y. Either f or m or n, all these are functions of two variables x comma y. That means f may contain only variable x or only variable y, or it may contain both x and y. The same case will repeat even for m as well as n also. Therefore either f or m or n, all these are either functions of x or functions of y, or it may contain both the variables x and y, right? Let us have few examples. Now in this case, suppose if I take dy by dx equal to, for example, 2x plus 3y. Now this is my f of x comma y, or I am writing equation like this. On another equation, e power x plus 2 into dx plus sin y into dy equal to 0. Now this is f of x comma y, this is m value, and this is n value. Note this, the general form of a first order and first degree differential equation. The general form of a first order and first degree differential equation is given by dy by dx equal to f of x comma y, or mdx plus ndy equal to 0. dy by dx equal to f of x comma y, or mdx plus ndy equal to 0, where f comma m and n, are functions of x comma y, Note these two examples, example 1 and this is example 2. Both are equivalent forms. Depends on situation. Sometimes I use this form, or sometimes I use this form, but both are exactly the general forms of first order and first degree differential equations. Now let us concentrate on equation like this, dy by dx equal to f of x comma y. Now we have a single task in first order first degree differential equations, that is nothing but finding the value of y in terms of x. When we discuss dy by dx equal to f of x comma y, that means what we are doing is we are finding change in y with respect to x. That means y is called a dependent variable. And x is called an independent variable. So in this case, we need to find y value in terms of x. Let us take simple example. Suppose I have an equation dy by dx equal to 2x. Now I want to solve this equation. That means I need to find the value of y in terms of x. Let us look at this. This is equivalent to d by dx of y equal to 2x. dy by dx of y equal to 2x. Now in this case, can you tell me one possible value of y such that whose derivative is 2x? Simple. Derivative of x square is 2x. Therefore, one possible value of y is x square. Because d by dx of x square is 2x, so one of this possible solution of this equation is x square. But is it the only solution of this equation? Certainly not. Some another possible solutions are like this: x square plus 9. Because when you find d by dx of x square plus 9, you get the result as 2x. Similarly, if you can write like this: x square minus 4. Similarly, you can write x square plus 1 by 2, etc. So all these are possible solutions of this particular equation. Got it? In this case, the solution is x square plus 0, x square plus 9, x square minus 4, x square plus 1 by 2. So all these constants I am writing as my own choice. There is no importance for writing these constants because the derivative of any constant is 0. Therefore, all these are solutions of this, and in general, the general solution of this equation is given by y equal to x square plus c. So this is the general solution of this particular equation where c is any general constant. Here I wrote particularly c value is 0, x square is x square plus 0, x square plus 9, c value 9, c value minus 4, c value 1 by 2. That means randomly I assign different values for general constant c. So instead of writing different constants, if I manage all this by a single constant, I call it as a general solution because c can be any constant. But in this case, if I assign particular value for that constant c, they are called particular solutions. So all this one, this and this, all these are called particular solutions of this equation. But this is called a general solution of this equation, right? Now, the thing is how to get the value of c. My question is how to get the value of c. Here I assign randomly for values of c, but how to assign random values? So is there any procedure to get the value of c? Yes. The result is yes, there is some standard procedure to get the value of c, and such problems are called initial value problems. Such problems are called initial value problems. So what is the advantage of this? These problems are useful in getting the values of general constants also. Since it is a first order differential equation, general solution contains exactly one constant. If it is a nth order differential equation, if it is a nth order differential equation, the general solution contains n constants, say C1, C2, Cn. And in order to solve all these n constants, n conditions must be provided, and such problems are called initial value or boundary value problems. My intention is always fixed. See, what is the input? The input means the thing which are giving to user. User means the people who are doing problems. So in computer terminology, I am using user, input, something like that. So the thing is, suppose if I give you one differential equation, what I expect from you is to get the general solution of that equation. If I solve first order equation, general solution contains exactly one constant c. If you deal with the second order equation, general solution contains two constants c1 and c2. If it is extended to nth order differential equation, the general solution contains n constants, for example c1, c2 and so on cn. Now in order to evaluate all these n constants, I need to supply n boundary conditions or initial conditions, and such problems are called initial value or boundary value problems. Now suppose, look at the same problem. The problem is this: dy by dx equal to 2x. Now randomly I assign c values 0, 9, minus 4, 1 by 2, etc. Because my general solution is this, and all these are particular solutions. All these are particular solutions because I assigned randomly some values for c. That's why they are called particular solutions. Now let us see how to get these solutions. I am giving one boundary condition. The boundary condition is like this. For example, y of 1 equal to minus 2. What does it mean? when x is 1, comma y equal to minus 2. Now in this general solution, replace y by minus 2, x by 1. Y value is minus 2. X value is 1. So 1 plus c. Therefore c equal to 3. So this is the way to get the solution. Like this, if I change boundary conditions, I will get different values of c. So general solution will be always fixed, but particular solutions will be infinite. That depends on boundary conditions. Hope you understand what we are going to do in the future sessions also. Throughout the differential equations, we have a single task, that is solving differential equation. So what do you mean by solving differential equation? Finding the value of dependent variable in terms of independent variables. Note all these points. Solving a differential equation is nothing but solving a dE is nothing but finding the value of dV. Solving a dE is nothing but finding the value of dV, that is a dependent variable in terms of independent variable. Solving a dE is nothing but finding the value of dependent variable in terms of independent variables. Note, the general solution of a nth order differential equation, the general solution of a nth order differential equation contains n constants. The general solution of a nth order differential equation contains n constants, say C1, C2, C3 and so on, etc. Cn. And in order to evaluate these n constants, n conditions must be provided. N conditions must be provided. Such problems are called initial value or boundary value problems. Such problems are called initial value or boundary value problems. One more note. If general constants are replaced by particular constants, then it is called a particular solution. If general constants are replaced by particular constants, then it is called a particular solution. Hope you understand what we are going to discuss in differential equations. Now let us discuss the various methods to solve first order and first degree differential equation, right? So the concept is solving first order and first degree differential equations. Solving first order and first degree differential equations. We have different methods. Let us discuss the first method. The name of this method one is variable separable method. Variable separable method, very important. Of course, it is very simple. Suppose the equation is this: dy by dx equal to f of x comma y. This is my first order and first degree differential equation. Now, as I mentioned in the title, it is a variable separable method. That means if f of x comma y is so flexible to separate x variables one side and y variables one side, then my task is very simple. Just separate the variables. the variables x on one side, variables y on one side. So that depends on the nature of the function f of x comma y. If f of x comma y is so flexible to separate variables x one side and y variables one side, then apply integration on both sides by adding a constant c. That becomes general solution of my equation, right? Therefore, if f of x comma y equal to h of x by g of y. So h of x contains only variables x followed by some constants. It should not contain y. G of y means it is purely a function of y. It should not contain x. Or you can have this h of y divided by g of x. Either this form or this form. Now I am going to explain the procedure for this case. The same thing you can handle even by this also. So f of x comma y equal to h of x by g of y. Function of x divided by function of y implies my equation is reduced to dy by dx equal to h of x divided by g of y. Now cross multiply this equation. This equation is g of y dy equal to h of x into dx. Now what happened is y variables are one side, x variables are one side. Now apply integration on both sides. Therefore, apply integration on both sides. We get integral g of y dy equal to integral h of x dx plus c. So just variables are separated. Apply integration on both sides, adding constant c. That constant c you can write even on left side or right side also. It doesn't matter. In place of c, you can write log c or e power c or sin c. That depends on problems. See, when we go through solving questions, you can understand what importance we are going to give for c. It doesn't matter. In place of c, you can write minus c, 1 by c square, e power c, particularly for finding general solution. In order to find particular solutions, then you must be cautious. But regarding for general solutions, in place of c, you can write c square, e power c, any constant. It doesn't matter whether you write c on left side or right side, whether on this side or on this side. So therefore, this is called equation 2, and this equation 2 we call it as general solution of equation 1. This is called general solution of equation 1. Hope you understand. Note all these points. Now let us discuss two examples on variable separable method. We discuss two examples. The first one is solve dy by dx equal to e power 2x plus 3y. Dy by dx equal to e power 2x plus 3y. Now let us see. This equation can be represented like this. This equation we can write it as e power 2x into e power 3y. Therefore, dy by dx equal to e power 2x into e power 3y. Now cross multiply this equation, we get 1 by e power 3y dy equal to e power 2x into dx. What happened is y variables are one side and x variables are one side. So integrating on both sides, we get integral e power minus 3y dy equal to integral e power 2x dx plus general constant c. Now this implies integral e power minus 3y is e power minus 3y by minus 3 equal to integral e power 2x, e power 2x by 2 plus c. Or this can be written like this, e power 2x by 2 plus e power minus 3y divided by 3 equal to c. Because when you take c on left side or right side minus c, that can be written as c. Now this is the general solution of this particular equation. Solve dy by dx equal to minus x divided by y. Dy by dx equal to minus x by y. Let us see. When you cross multiply this equation, it becomes y dy equal to minus x dx. Y variables one side, x variables one side. So integrating on both sides, we get integral y dy equal to minus integral x dx plus general constant c. This is equivalent to y square by 2 equal to minus x square by 2 plus c. Now this is nothing but x square plus y square equal to c. But in place of c, you can write c square also. I will tell you why I wrote c square in place of c. If I change different values for c, then what happens is all these curves represent family of circles. X square plus y square equal to c square. Suppose if c value is 1, it represents a unit circle. If c equal to 1, the circle, this is my circle. So radius is 1 unit. If c equal to 2, slightly it increases another circle. So radius 2 units like this. Therefore, when I change frequently the values of c, I get a family of circles. Family of circles. Even in the examination, they were asking the general solution of this equation represents a family of different options are giving like frequently. So you need to understand, a student must have awareness about the straight line curves, circles, parabolas, elliptic curves, etc. Okay, note this point. So please note one point. Here the solution curves represent family of circles. Here the solution curves represent family of circles. Now this is end of method 1, variable separable method. Now to discuss method 2, we discuss one definition. That is homogeneous function. Homogeneous function. Suppose we have a function f in two variables x comma y. There is a function f in two variables x and y. We say that this is a homogeneous function. We say that this is a homogeneous function if f of kx comma ky equal to k power n into f of x comma y. So whenever this happens, that is f of kx comma ky equal to k power n into f of x comma y. K is some general constant. Replace x by kx, y by ky. You must get k power n into original function f of x comma y. Now here n is also some constant, and that n is called degree of this homogeneous function. One of the important property of a homogeneous function is its degree. So because of the degree, we can have many properties. One important property is the degree of a homogeneous function. So when you replace x by kx and y by ky, you must get k power n into original function. In that case, it is called a homogeneous function of degree n. Let me tell you why we got the name homogeneous. Generally, homogeneous means the same powers. But generally, to get the homogeneous function, it is not necessary that powers of x and powers of y are same. But when you group them, when you take it back, the powers of x and powers of y indirectly will be same. So therefore, whenever this happens, then this is called a homogeneous function. Because of this k power n, we call it as it is a homogeneous function of degree this n. So this n is a constant. If this happens, it is called a homogeneous function of degree n. Let us take an example. Suppose f of x comma y equal to x square plus y square. Simplest example. Replace x by kx, y by ky. The result is kx whole square plus ky whole square. And this is k square x square plus k square y square. Therefore, this is k square into x square plus y square. This is nothing but original function f of x comma y. So therefore, this is k square into f of x comma y. Therefore, this is what? F of kx comma ky. So when we replace x by kx, y by ky, the result is this. Therefore, in place of n, we have a number 2, and that number 2 we got because of equal powers. But to get homogeneous function of degree 2, it is not necessary that powers of x and powers of y are same, or to get power 3, something like that. Let me tell you one more example. Suppose if I have f of x comma y equal to, for example, x square y minus 2y cube. Now when you replace x by kx, y by ky, the result will be like this. You can verify k cube into f of x comma y. Replace x by kx, y by ky, k square x square into ky, that is k cube. Replace y by ky. You take k cube common, then you will get the original function f of x comma y. But in this case, powers of x and powers of y are not same, but still we got the degree of, it's a degree of 3. Therefore, this is a homogeneous function of degree 3 and it is a homogeneous function of degree 2. Note this definition. A function f of x comma y, a function f of x comma y is said to be a homogeneous function of degree n. A function f of x comma y is said to be a homogeneous function of degree n if f of kx comma ky equal to k power n into f of x comma y. If f of kx comma ky equal to k power n into f of x comma y. Note this example and that as example number 2. So it is a homogeneous function of degree 2. It is a homogeneous function of degree 3. Next definition. Homogeneous differential equation. Homogeneous differential equation. Suppose we have an equation like this. Dy by dx equal to f of x comma y. This is a first order and first degree differential equation. We say that this is a homogeneous differential equation if this RHS function is a homogeneous function of degree 0. If RHS function is a homogeneous function of degree 0, then this differential equation is called a homogeneous differential equation. So we say that dy by dx equal to f of x comma y is homogeneous differential equation if f of x comma y is a homogeneous function of degree 0. Let us have one example. Suppose I have dy by dx equal to x by y. Now look at this is f of x comma y. Replace x by kx, you get kx. Replace y by ky, you get ky. Kk will get cancelled. What does it mean? When you replace x by kx, y by ky, it turns to k power 0 into x by y. So it's a homogeneous function of degree 0. One simple logic is numerator function is a homogeneous function of degree 1. X is. It is alone a homogeneous function of degree 1. It is alone a homogeneous function of degree 1. Because of that division, overall function is a homogeneous function of degree 0. Suppose if I have x square plus y square in the numerator, in the denominator x square minus y square. Say, for example, if I have this dy by dx equal to, for example, x square plus y square. For example, in the denominator I have, for example, 2xy. Now you can see it's a homogeneous function of degree 2. It's a homogeneous function of degree 2. Because of this division, this is a homogeneous function of degree 0. Hence, it is called a homogeneous differential equation. It is a homogeneous differential equation. Note this. A differential equation dy by dx equal to f of x comma y. A differential equation dy by dx equal to f of x comma y is said to be homogeneous. A differential equation dy by dx equal to f of x comma y is said to be homogeneous if f is a homogeneous function of degree 0. If f is a homogeneous function of degree 0. Note this and this example. First one is dy by dx equal to x by y. Second one, dy by dx equal to x square plus y square by 2xy. Now our next task is solving homogeneous differential equations. That we call it as method number 2. It seems to be complicated. You can't solve it by method 1 because of this plus you cannot separate x square and y square. But you can handle this by separation of variables also. So when you want to solve this question, you can apply method number 2 or method number 1. Method number 2 I will discuss shortly. That is called as solving homogeneous differential equations. But if you want to solve this, method 1 is not possible. If you want to apply method 1, variables must be separated. But between x square and y square, there is a plus symbol. So you can't separate x and y. Right? So our next task is solving homogeneous differential equations. That is method number 2. So next one is method 2. That is solving homogeneous differential equations. Solving homogeneous differential equations. Right. Suppose we have an equation dy by dx equal to f of x comma y. I want to solve this equation. Now assume that this is equation number 1. See, if I able to separate x and y, my job is simple. But sometimes it may be possible, as I discussed in the last, in example 1, it is possible. In example 2, it is not possible. But let us try to solve this by separation of variables by the indirect method. So if I want to solve this, I take y equal to vx. Call it as equation 2. That means y is a current dependent variable. It is transformed to new dependent variable v. But there is no change in x. X is independent variable. I am not changing this. Current dependent variable is y, but it is changed to new dependent variable v. X is independent variable. It is not changing. But dependent variable is y. It is changed to v. Now differentiate equation 2 with respect to x. We get dy by dx equal to apply product rule. This is a variable, this is a variable. So v into d by dx of x1 plus x into dv by dx. So therefore this is v plus x into dv by dx. Now you call it as equation number 3. Now in equation 1 we have dy by dx. In equation 3 also we have dy by dx. Therefore when you compare equation 1 and equation 3, that is from 1 and 3, we get in place of this dy by dx, we are writing v plus x into dv by dx. So this is v plus x into dv by dx equal to f of x comma this y is replaced by vx. Now this is equation 4. Now let us see, this equation 4 is flexible to separate the variables v one side and x one side. See, just to separate the variables only, we have taken y equal to vx. Got it? We have taken this y equal to vx to separate the variables. But don't take y equal to vx to solve any differential equation, any first order equation. If it is a homogeneous function of degree 0, that is if the equation is a homogeneous differential equation, then when you take y equal to vx, definitely variables will be separated. So we have taken this y equal to vx to separate the variables of v and x in equation 4. Therefore, in this case, now solve equation 4 by variable separable method and replace v by y by x, and that becomes the general solution of this equation, because when you solve this equation 4, the general solution will be in terms of v and x only, but the question is given in terms of variables y and x, so finally v must be replaced by y by x. In 99% cases, when you are handling homogeneous equations, we prefer this y equal to vx. Another useful transformation to solve homogeneous differential equation is x equal to vy, but this is a very rare occasion. In 99% cases, we take this y equal to vx. Now my question is, when we take x equal to vy, if dy by dx is a complicated expression, then take the reciprocal of that, dx by dy. If I have a first order first degree differential equation just like a dx by dy, then take x equal to vy. See, when you are taking x equal to vy, x is a dependent variable. When you are taking y equal to vx, y is dependent variable. So whether it is dy by dx or dx by dy, my goal is simple. Current dependent variable is changed to new dependent variable. In both the cases, I am not changing independent variable. Note this point, very, very important. Got it? So therefore, in most of the cases, we take y equal to vx, or in rarely we take x equal to vy. If I take y equal to vx, the general solution will be in terms of y by x. If I take x equal to vy, finally v is replaced by x by y. In this case, the general solution will be a function in terms of ratio x by y. Therefore, when you handle a homogeneous differential equation, general solution contains the ratio terms either y by x or x by y. Not this. Note, another transformation to solve homogeneous equations is x equal to vy. Another transformation to solve homogeneous equations is x equal to vy. One more note. The general solution of homogeneous equations contains the ratio either y by x or x by y. Contains the ratio either y by x or x by y. Hope you understand this. This is almost part of method 1 only. But in the starting level, we were unable to separate the variables x and y. Right? Now we discuss 2 examples. Let me start with a simple example to solve homogeneous differential equations. Suppose if my equation is dy by dx equal to y by x. So it is a homogeneous function of degree 0. Power of y is 1, power of x is 1. Both are homogeneous functions, numerator and denominator. So combinedly, it is a homogeneous function of degree 0. So take y equal to vx. Therefore, this dy by dx becomes v plus x into dv by dx. equal to y equal to vx, vx by x. So this implies v plus x into dv by dx equal to this is v. So this v and this v gets cancelled. So the result is x into dv by dx equal to 0. This implies dv by dx equal to 0. So this implies this is what basically d by dx of v equal to 0. This implies derivative of something is 0 means it must be constant. So v equal to c. But what is v? Y by x. Therefore this implies we got y equal to cx. So this is the general solution of this equation by method 2. If I can handle this by method 1 also very simply. If I handle this by method 1, then cross multiply this, you will get 1 by y dy equal to 1 by x dx. Variables will be separated. Apply integration on both sides. Integral 1 by y dy equal to integral 1 by x dx plus c. So this implies log y equal to log x. This c I can write it as log c. Even if you do not write log c in place of c, it doesn't matter. Solution doesn't change. So therefore log y equal to log a plus log b. This is log ab. Apply anti-logarithm on both sides so that logarithm terms will be cancelled on both sides, so that my solution is y equal to cx. So this is the way to solve this by method number 2. That is homogeneous method, and this is by separation of variables. See, whatever the method you follow, final general solution must be same. Note this. This is the end of the session. We continue next question in the next session, right?